everyone. I welcome today's guest. Welcome, sir. Thank you for accepting our invitation. Welcome to the session on precast construction, advances in precast construction. Welcome, sir.
Thank you.
Good afternoon to the participants. I feel privileged to introduce today's speaker, Srinivas Satyanarayan. Srinivas Satyanarayan sir has completed his BE in Civil from Bangalore University, MS in Structures from SDSM and IT, Rapid City, USA. His professional experience are combined experience of 25 years worked in USA and India. Started career in IISc in Soil Mechanics Department, worked in fly characterization and have published 2 international papers and 3 national papers. Was structural engineer for Rail and Transit Metro Rail Structures, New York, World Trade Center, WTC Park Station. He was a project team lead for BARC project, principal engineer for Bangalore Metro, Majestic Station, multi-level and underground station. Design project manager in Wipro, assistant design head in Ketera for precast structures, and currently sir has started his own company, Consoles Engineering Services, with emphasis on design build solutions in precast, especially in precast. Achieved in building a villa in 15 days. Sir has been awarded for the design excellence for BARC project in 2012 at Potential Service Consultants. Sir has been awarded with Design Excellence Individual for services at Wipro Limited. Sir is a member of American Society of Civil Engineers, ASCE, Chartered Engineer, the Institute of Civil Engineers, India, Structural Engineer, Registered Engineer for BBMP. With this, I welcome you, sir, for the session on advances in precast construction. Thank you very much and for accepting our invitation and welcome. Over to you, sir.
Yeah. Okay. Thank you all. Thank you for a very good introduction. Good afternoon, all who are participating in this presentation right now. So, I first of all, I would like to thank the AICTE Training and Learning Academy for arranging this kind of a presentation, and BLDA College, Vachana Pitamaha Dr. PG Helkatti College of Engineering and Technology, and Principal Dr. Atul Iyer, then Naveen, Professor Naveen in Desai, Professor, I think Ijaz Zande, if I'm spelling it right, I'm sorry, and also the coordinator in between, Dr. Asif Iqbal Mohan. So today let's just have a kind of I think like a lot of people would have started hearing about precast construction happening around, and it's been extensively used in infrastructure construction. But today, I think like I would definitely concentrate only on the building sector, how the precast technology is used, and this approach is actually a kind of approach what an industry is like in an industry would actually do this. So there's a bit of technical design aspects what I really deal with. But before that, I think like I would give a brief introduction, like what all things we really consider, and how are these elements produced, what is the procedure, then we go a bit of the design, then the handling techniques and everything. So this will be a brief of what this presentation would be. So let's start off with this. So the precast technology in building construction mainly is like nothing but using different structural components or elements, and these elements are actually manufactured in a controlled environment using advanced construction materials and techniques. The elements are connected with special connections. This is one of the most important things without which nothing would really work with. So the special connections are the ones which really make the entire structure monolithic, and this is what we could really expect for. So when we are looking at such kind of precast construction, one has to be very, very careful with all kinds of elements and its connections. So why are we looking at precast when we have a very good I think like the cast sensitive construction going on, when a lot of people really working on this. The first of all thing is like there is always dearth for skilled labor. So with this, what happens is you always kind to resort with some kind of an alternate construction. I think like the answer would be something like a precast for that. Apart from this, the developers are also looking for to adopt modular technology so that they can save a lot of time. And the always the ask is definitely the superior quality what they would require sustainable products and durable thing and with more aesthetic kind of appearances. So, with all this ask and also the current pandemic, whatever we are looking at, there's a lack of manpower, and the smart way to really work with to achieve all such required things is, I think, like is precast construction, and that would be need of the hour. So let us just see what all kind of benefits first what we are getting with the precast construction, so that we'll understand exactly why this has been adopted nowadays. So first of all, I have already mentioned you like the kind of like labor intense what you see in the in the cast sensitive construction. What happens is like usually when we are constructing a kind of some buildings, you will see like hundreds of people just walking around and everything, and there'll be a lot of activity happening. On the other side, on the right hand side, what you see is a precast construction. Here, one can also see that a multi-level construction is happening compared to one what is happening on the other side is on a single level. Apart from that, you would see very less labor intense. It is like some machineries which is going on there. And apart from that, I think like a site like such things, like maybe if you're talking about 10 lakh square or a 6 lakh square feet kind of this thing, I would say that not more than about 50 people, including the project manager, all the engineers, the laborers will be there on site. So on site, especially for the erection, I think like you'll hardly see about like 10, 15 people. Rest all will be just managing some things. So this is the kind of first advantage what we really get from the precast. The next thing is the logistics. So in cast institute construction, we have to store a lot of materials. It has to be protected properly. Whereas in precast construction, I think all we have to do is like just store the materials required for that level of construction, and it would require some space. That is more than it, and then the crane is a major kind of equipment which has to be used in precast construction. And I think like cranes will also be used in the conventional construction. The only difference is I think like we'll have a little higher capacity cranes here. This is one of the things what we have a difference here. And the scaffolding, I think like when we definitely think about conventional construction, you will have a lot of scaffolding materials to really deal with. You'll have to support the members, then again de-shutter that. All those things happen, and you'll have to even go back and for any kind of other work, you'll have to again put some of the scaffolding. But here in this kind of a system, I think like we don't need scaffolding materials at all. I think like it'll be designed in such a way that it can be self-standing and will really help optimize the costs. And definitely, the quality is what we look at always. It is not that just to say that the cast institute construction is very poor in quality. I mean, it's just a photograph what's depicting here. There are a lot of constructions which has really come up good. But what happens is in cast institute constructions, people or the designers or even anyone take a little liberty because they'll have a lot of chances to do some more changes during construction, and this leads to a lot of like kind of like chipping in, breaking in, all those things. Whereas in precast construction, I think like we will take care of all these things much ahead of construction. I'll deal with this a little later. So whatever the finished product we really get in, I think like it'll be a wonderful product which comes in. The one what hello, yeah, the one what you see is there is like one of the hospitals which has been built. Apart from this, I think like the curing, what you really achieve, since it's a very highly controlled product, whatever we get in, I think like the controlled environment really makes the precast a very good material, and you don't have to literally spend anything on kind of like doing any kind of curing or anything further. So, what are the common materials or the elements which will be used in building construction? The first thing is like the columns itself. The columns shall be like corbel based, and it will have some sleeves and everything. These are some photographs. What you see here, there are beams. Beams will be usually like uh, what you see there, and there are walls. Walls can be like a solid wall or a double wall, what you see here. A double wall is one wherein you'll have two layers which will be connected with a kind of a truss material or a. So this one will really help to reduce the weight of the material. And once installed, I think that whatever is there can be filled with concrete. This is very useful, and I think like a lot of builders or like the precast contractors really prefer this kind of a wall because it is easy to handle, and the connections what really comes with this kind of a wall is pretty easier than what you see on the above, which is like a solid wall. Solid wall is like more robust and also like a little heavier. But I think like these are the walls which really help the structural engineer to use it as either as a core wall or whatever is there. So it's always a give and take what we have to do. Apart from this, we also have hollow core slabs. Hollow core slabs are one of those things where it is pre-stressed kind of slabs with a hollow in between. And these labs are very, very useful and very efficient enough for a kind of building construction. It can be used for longer spans and definitely reduces the dead weight of the building also. And apart from that, we also have staircases, which is like what you see there. These are some of the products what we use. There will be something more, but I've just taken the main elements. So further than whatever we see as the structural elements, there are something like what we also use it as an architectural element. One can use this as a finished product. The walls, whatever I was showing you, the solid walls, I think like you can also have something called as a graphic concrete. A graphic concrete is something like it is it's a technology that transfers the custom or stock images. You can have
கேட்க மாட்டேங்கிற போன்ல சார் ஒரு நிமிஷம் பேசுறதுக்கு இறங்கு இங்க பாரு இறங்கு
I think like somebody should mute in. I think we are getting a lot of other noises.
I muted, sir. I muted.
Um, Graphic concrete is something like what we can customize any kind of patterns. So this kind of patterns is like you don't have to literally have any kind of painting on this. There are a lot of things what we do. I think like I will just discuss this in a little next slides. These are like surface data printed on a special membrane. The membrane is actually manufactured in Finland, and you get these kind of membranes, and it is laid on the table, and then the concrete is poured on that one. Once the concrete is cured and extracted from the form, the membrane is just taken off, and the retarder is pressure washed away. All you have to do is just give a kind of a pressure wash, and you will see the patterns revealing itself. You can see the contrasting fair faced and also the aggregate face just coming out, and you can see the images on the left hand side where it almost depicts like a kind of like a forest or whatever is there. There are a lot of other things which can be really done with graphic concrete. Apart from this, there is also kind of like called as concrete form liners, which is called as Reckley forms. These are like rubber-based kind of forms, wherein again it can be used for repetitive uses. Whereas the the graphic concrete is like one kind of a use. Like once you just use it, I think like once the pressure wash is done, that membrane is gone. You'll have to have another roll of paper or whatever is there to be laid. But in directly, that's not a case. You have a lot of other patterns. One can actually get into this website, and whoever is interested in can look into that. You get a whole variety of forms, which gives you beautiful patterns. And these are walls where we usually use for the facade kind of construction. So all these products are actually like will be manufactured in a controlled environment. That is what I was saying from day one. I mean, from the earlier slides. So one can see the column molds. Column molds are one what you have like it runs in lengths, and it can be adjusted. You can see that picture here where you can use the kind of side shutters which can be adjusted to the sizes what you require. And it is also a kind of like a even kind of a shutter which can just go all the way down. In precast, one has to literally have a kind of a very good knowledge of what plant you're dealing with. The reason is all your members or whatever is there has to be designed according to the limitations of the plants. So a designer has to keep in mind what plant limitations are, and based on that, I think like his member sizes has to be also in accordance to that. So the next one is the Holocaust bed. The Holocaust bed usually is like around 100 to 120 meters long, with pre-stressing strands and abutments on either sides. So these hollow core slabs are like pre-stressed, and there will be like retarders which will be used. I'm sorry, the kind of machines which will be used, wherein you can just get the hollow core out. Apart from that, there is also like wall mold panels. These panels or casted on steel frames, and it will have vibrators at the bottom so that you get a very good beautiful surface. And similarly, the double molds or the double wall molds are also done in a similar way. The next is the solid slab, very similar to what you have seen in the Holocaust slab. Here, you may not find the pre-stressing strands, or you can also go ahead and do this. That's not a problem. You can do either pre-stressing solid slabs or just a normal solid slab. Apart from that, beam molds, then again with the pre-stressing kind of a unit here, then the staircase units. This kind of a facility will be usually like a lot of in kind of a capital has to be required to really install all those things, and then to go ahead and invest on that. But alternatively, there is also like a way where we can have a mobile plant. A mobile plant is a kind of like an intermediate solution wherein we can have a lot of wall panel molds, just as shown here. What you can do is like you can use the site itself, and get some steel material and use the wall panels done as there, and then based on that, I think like we've already seen that how I mean the photographs here shows that the boundary walls, how they've been casted, the drains, and there are a lot of other things. I think like what we are doing right now is on a similar basis, that we use the existing site, which requires a certain amount of space. So we put in all these molds there, and concrete is casted there, and directly installed as soon as it's ready to be installed. The advantages of this one is like you will save a lot of logistic cost from the factory to the kind of site. If one has to transfer all those things, the cost involved in that. But in a mobile plant, I think like you can definitely get away with that. The only kind of other limitations what you have is like you may not find a pre-stressing bed here, which has to be actually you will have to get it from the factory itself. So let us just understand how the precast construction flow would be. The first thing is like the design information and coordination. The design involves three stages, that is design information and coordination, the structural design, and the 3D model production drawing. These three forms the first part. Here one has to really understand that once you're doing the structural design, along with that you'll have to have a lot of coordination with your services so that everything is getting accommodated in. This is where that 3D model production comes in, so that you can have a kind of a view. um, there should be a kind of a harmony between the structural elements and also the MEP requirements. So once you have all those things, the member sizes and all those things gets freezed up. So with that, I think like there'll be a kind of a shop drawing production which goes to the element production. Then usually what we do is like the foundations will be cast in place. So it's usually after the foundations are done, the members will be transferred to the site and the installation happens, and the finish and handover is the execution part. So whatever we see is like this kind of processes, like these kind of buildings which are like totally precast. So one can see this is again a kind of like a graphic concrete. What you see, I think like this is a very popular building throughout Karnataka, and this is completely concrete based. There is no paint, nothing involved. This is graphic concrete. The graphic concrete is also here. The rest of it is like kind of like Recley forms what we have used. So after this, I think like we'll just start on like how a design process or what all design would really require in a precast kind of a buildings. I'll just briefly tell about all these things because there's it's a vast industry, and every person will have his own kind of methodology to really design a building. And I'm sure that everyone will have their own ethics to follow. And the thing what we generally follow is like uh, there are like a lot of methodologies which is like listed in PCI and everything. But here, with the conducive environment, whatever we have to get the cost as low as possible. So we deal a lot of with wet connections. So I'll be dealing with such kind of connections which are like almost easy to produce inside, and also like far more economical than what you use like very ready-made connections and everything. So the next coming slides will be dealing with all those things. So the precast construction is definitely far different from what a conventional reinforced concrete structure would be. The first thing is like what we have to take into mind is like we can't just go ahead and say that every building can be built with precast. One has to ensure that the building which is where the building is being built, the kind of whether the site and the surroundings can accommodate some kind of heavy traffic vehicles, and also like we need to see whether like when I want to transport some kind of what is it elements, a 40 foot kind of a trailer should actually come and dump all those materials and all those things. So we'll have to first have that feasibility kind of thing. Then we have to see whether there is any other kind of services or like electric lines and all those running, because there will be some crane equipments which will be running across. So generally, what happens is a precast construction may not happen in a constrained space. So it would require a kind of a little space where it can spread its wings, and it can we can usually have a kind of a very good construction. The typical floors. Other thing is like what we do is like during design, probably like we always say that we have to optimize on things, and we start like having so many members uh, saying that this is the optimal kind of a thing what is required. But in precast construction, we'll have to limit those things because we need to have a kind of elements which can be reproduced, and also like reduce the production of like having so many molds and all those things. This will really cut down the cost. The other thing is like we would require a little higher strength concrete. The concrete also should be in a very good quality, and the reason is like once it reaches about like 50% of the concrete, like whatever we do, it has to be good enough to lift those materials as soon as, because I need to demold the members very fast. I think like say within a day. Else, if I'm just putting, putting the element on the bed for about 2 3 days, then I'm losing time. So what we do is like we deal with some high strength concretes so that it achieves the required strength for lifting, and then the next day we just lift it off, and then it will be placed at least for a curing for about a little while so that it can be used for the service loads. So what happens is like if I use non-typical inverses, like definitely there will be a cost overrun. And the other way is like we also want to achieve some bigger spans. So one of the way is like definitely using the pre-stressing technology, and we'll have to see all those things much before when we are doing it. All those things has to be seen very much in the planning phase itself. Now, whatever we do is like the first thing is like when we pour the concrete on any table or any kind of wall, the first thing what we have to see is like the early strain grain, so that it can be demolded easily and can be the mold can be accommodating the next kind of casting. So this process actually involves when there will be an initial load in the early strength. So prior to its use, the concrete initial strength are used. So there will be some tension steel, whatever is there for the following. The strength of concrete will be usually around 8%, 8 to 10%, or within that for compared to its compressive strength. So cracks tend to develop at an early stage of loading in flexural members. So hence, one of these things to reduce these things will be like using pre-stressing method to counteract that. To prevent such cracks, I think a compressive force or the pre-stressing force can be suitably applied in the perpendicular direction. Pre-stressing enhances the kind of like bending or shear or the torsional capacity of the flexural members. Further, we have to also have the section should remain like uncracked under service load. So this leads to like whatever when you do the pre-stressing, this can increase the durability. It gives proper stiffnesses and also less deformation when you do the lifting procedure. It also increases the shear capacity also. Improved performance under dynamic and fatigue loading also is also being seen. So usually when we do materials without pre-stressing, I think like you will see a very less kind of a span to depth ratio. Whereas when you do pre-stressed structures, I think like or like slabs, you have a higher depth span to depth ratio. Um, Also, like doing using pre-stressing kind of a technique, we can reduce the self weight, and then it can help in better quality, reduced maintenance, and also like repetitive construction. This is where I was like just really stressing about. What we actually have to do is like when we design either beams or slabs, we need to have a similar kind of a strand pattern, because we are using longer beds and everything. I can't have a different beams or like different strand patterns for different beams. So we need to standardize those things such that the most of the beams or whatever is there is like having a similar kind of strand pattern. If not, what we have to do is like in such cases, we still use a similar strand pattern, but if the beam would not require so many strands, I think like we have to debond them. So that is another way of doing it. So the compressive strength of concrete is always like around M40, and we use like all the tensile strength of the steel, whatever is there, the tendons is like much higher than whatever you see. So what is the framing system we usually follow here? As I said already, the foundation shall be always a cast sensitive kind of system. I'm just talking about some kind of a commercial buildings where I think like we cannot just go ahead with the foundation with a precast. So the foundation will always be cast sensitive. The basement walls, whatever we use, the most preferable will be like a double wall system, which will be easy to install. So what they do is like the dowels from the foundation will be protruding out, and the double walls can be installed very easily, and the concrete can be filled in. This gives a very good effect, which will be very similar to what we see the basement walls. Or if this is not possible, because at some times what happens is double walls, there is some limitations with respect to kind of like the seismic zones, providing more shear links and everything. There we'll have a little kind of a limitation. In such cases, I think solid walls will be definitely used. Then the column with corbels, you can definitely see here, like whatever we do here is like the columns will have corbels, which will support the beams on the corbels. The beams, what you see here, these beams are usually L-shaped on the periphery, and it will be like inverted in the intermediate spans. So L-shaped is to like accommodate the slab on one side. The internal beams will be T-shaped so that it can accommodate the slab system on either sides. So one is like other thing what we have to also see is like there are different kinds of ways where we can design the beam. So whatever you see here in the photograph is like you're seeing a double or a triple height column. What you see here or here, definitely you are not able to achieve any kind of a moment connection here. So this is more or less like a hinged beam, whatever we are looking here. So accordingly, your designs has to be taking care of this. So probably your system would be like where the core walls is taking all the shear or whatever is the lateral system itself is. Apart from that, you will have the slabs. These are the slabs here, the hollow core slabs, which are spanning between beam to beam. And usually you can use a hollow core system right from like around 6 meters to even 15 to even, we can actually increase even to up to 18 meters. But the hollow core size just increases. But ideally, I think like I would say around 12 to 13 meters is what we have extensively used, and 15 meters can be used. So these are like it will be simply supported between the the beams. Apart from that, you will also use like the solid slabs, or the half slabs are also being used where the spans are much lesser. Core walls are as I've already told, it can be solid or a double walls, which will be spanning floor to floor. Design process. So what are the the major steps we really follow in the design? The first thing is like as I've already briefed you, the framing layout will be one of the most important things what we have to deal with. So we need to decide what kind of system what we are building in, and we need to have a framing layout. Preparation of a DBR, I think like we do it for every kind of construction. Then modeling and analysis. So here what we do in precast construction is we just model the structure as we do very similarly for the cast scissor construction. There is nothing special what we do. This will be the first cut kind of analysis. So all the members, whatever we take, shall be designed as we do in cast in situ. But wherever the slabs are coming in, we shall assign them as a single or a one-way kind of a slab. It will be spanning in only in one direction. You cannot have a two-way kind of an action here. Uh, Check for all the code requirements. This is very thing, and then check for the element design, the foundation design. What we do normally, it's very similar. Then what comes is like the preparation of a 3D model, which elaborates every detail to perfection. So, based on whatever is there with the coordination, what happens with with the MEP team and everything, a 3D model will be developed. So after this is where the real kind of a design starts. So every element has to be given an ID with, and the element design has to be proceeded with. So with this, I think like there'll be shop drawings which will be generated, incorporating all the MEP inserts also. We have to take care of this because we cannot go back and start doing any MEP inserts later on. So to the maximum extent, I think like we have done this and it can be easily done. So what are the code requirements for basic design? I think like I don't want to list out all the codes here. I just told what are the main codes which is required here. So all codes related to RCC design based on our IS standards. Then the other code references what we really go with is like ACI 318, then the PS 8110, and also there's a PCA handbook. I think like there's a latest edition also. I think maybe an eighth edition. I think I've just written seventh here. So PCA handbook, which is like a very detailed book for the precast and prestressed concrete. This gives a lot of insight in all kinds of connections, how the construction has to be made, and most of it is actually like derived from the PCA handbook, and we try to like adopt it for our codes. So these are the one of the main kinds of references what we really make. So what are the concrete grades we generally use? I think like footings is like around 30 PA, then the columns will be around 60 or even 40. The shear walls also will be shear walls, retaining walls will be around 40 MPa, staircases and all those things. Anywhere we use pre-stress or something, that is where we go up to like around 60 MPa. So that is like the Holocaust slabs and the pre-stress beams. Again, there'll be a topping on any kind of slab system what we adopt in, which will act as a diaphragm, and that will be usually around 40 MPa. So, what is the advantages of this Holocaust system? Suppose if you see in Holocaust, which is like around 160 uh, kind of a thing, it is 160 kind of a height. When you see the effective thickness of that one, it will be like almost like around 101.9. That's the kind of a thickness what it reduces to when you compare it to the solid slab. So definitely when you compare this one with respect to the solid slab, the weight of the Holocaust is always lesser. So how do we know this? So there's been a kind of like what I have just analyzed on all the structures. So I have done a kind of like study where a typical flat slab is there, the conventional structure, compared to what the same system, the same building, we have just used hollow cores with some beams. So if you literally take the kind of the slab to slab comparison, actually there was like it will be like around 41% lighter, and it is also energy efficient. If you start using, I did not go ahead with any pre-stressing strands for the beams here. So if you start using that one, I think like it will be far more lighter. I think like around 15% lighter when you start using pre-stressing technique. So in overall, what happens is like when you see the mass of the building, when you compare between the precast and the cast in situ, there is about like the building is almost about 20% lighter. So this is one of the most good advantages what we can really take in and have some good optimization done. This we have to see with the geometry and everything, and definitely using hollow core will help any structure to reduce the weight. So we were talking about the hollow cores. The other thing is like the half slab itself. The half slabs are nothing but these are like they call it also as filigree slabs. You have trusses or like something like a shear connectors which is on the top of the slab, and the slab. Suppose if you require about like say 150 slab for any kind of span, usually what we do is like we cast about only 90 somewhere around that area, which can take care of all the initial loads. That is nothing but it should satisfy for the lifting criteria. So once this criteria is done, I think it will be placed on the frames wherever you intend to. The rest of the concrete has been just concreted over on top of it. So the slabs will be good enough to take the loads for the construction loads and also the lifting criteria. This is what we have to really uh, look into when we design this kind of a slab. This kind of a slab is very much used in kind of like small constructions. Holocaust slabs are not preferred in residential sector because you will see kind of a grooves between each and every hollow core. What happens is the hollow core is like about 1.2 meters wide. That is what the bed allows you to really cast in. So such kind of things you'll see a kind of a groove, which I think like most of the people may not prefer to see in the ceiling. So in that cases, I think like we can go with this kind of a design, a half slab design, wherein you can cover the entire room, whatever is there for the residential sector, and still suffice the precasting needs. So let us get into a very important topic of the precast construction connections. So I don't want to scare you with whatever you're looking at there, but it is just like kind of like the intensity or the kind of like seriousness what we need to really have when we are designing such kind of structure. Since we are actually doing element by element and it has to be connected properly, I think like corrections will be one of the most important things what one has to really give importance to. So the connections will be the backbone of the structure. So any negligence in analyzing these things, or you may see some drastic kind of results like this. So one has to properly understand how the stress flow or how the load path is there in this particular structure so that the connections are designed accordingly. If you don't, that is what you see here, and every element must be connected such that the entire structure behaves monolithically. So let us start off with, excuse me, the first thing what we really want to start off with is like a foundation to column and a column to column connection. See, whatever we analyze from the ATAS or whatever we get or any other software, I don't want to really call it as ETAMs. So whatever software we really use, uh, the column steel is extended into the footing so that it acts monolithic. In a similar way, what we do is like the doubles will originate from the foundation. One of the important things what we have to see here is like uh, there is a kind of like what we do is like in usually in columns in the midway what we do is like we do a 50% kind of a lapping, but in precast construction this is not possible. Or so since the rebars will also already be in place, the lapping happens at a same zone. So if you refer to SP24, when the lapping is at a same place and there's each and every bar getting it's continued at the same this thing, the kind of LD what you have to follow is like around 1.7 times LD. So apart from whatever you do, so it'll be a little lengthier, and you'll be I think probably like wasting a lot of steel with respect to that. So instead of that, one can go with a grout coupler. A coupler is is just about like maybe about 300 to 400 in length, and it will have a kind of a threading on one end so that you can have your rebars threaded here. The other this thing is like where you can have the rebar getting into the grout coupler. So once it gets the free end, I think what we do is like there'll be a grout which will be poured through this, and the entire uh, rebar gets locked. So if you see, this is the kind of a typical kind of a connection where there'll be a column which is below and a column which is above, and uh, it just goes inside, and then you will have the grout couplers where the apertures are, where you can just fill in the grout, and it fills out, and then it gives you a complete connection. So uh, this is a way of doing it, and nowadays a lot of grout couplers, which is like, I think, like if you have anything more than about like 15, I mean 16 to 20 depth, I think like it almost matches up with whatever the kind of laterals we are using. So this will be much more or a better use in kind of our construction. So how are we designing this wall dowels? So the first thing is like whatever we get, I think like we'll be getting the percentage from the ATAS model. So the cumulative shear, whatever we get, has to be calculated. So what we do is like it will be a sum of the in plane and out of plane shear. The out of plane shear may be like maybe due to any soil pressures. So the effective shear is nothing but the cumulative shear, and also whatever is the dead load which is also acting, we can just use that one as a kind of to reduce the steel. So what we do is like we can reduce the steel by using 0.45 times the dead load of the ball, and then the effective shear is calculated as shown. So the PT is calculated as a final percentage and provided as a double. So in case of double walls, we can easily provide two doubles, which will be very easier to provide. But whereas in case of a solid one, there'll be a single dowel provided. So one has to calculate that particular dowel accordingly. I'll just show how the connection looks in. So this is how the detail looks in. So when the solid wall is there on the right hand side, you will be only the reason is you can only accommodate one kind of a double in any kind of solid wall, unless it is a very wider wall like around 350 or the same. Usually, I think like the sleeves will be around uh, 70 to 80 in diameter, and you will have the covers, you will have other rebars going in. You cannot just go ahead and just put two dowels in between that. So that's the reason the dowels will be little, whatever we do in solid walls will be of a single dowels, and then in double walls it's easier to accommodate two dowels, and that is how it's shown here. And one has to also make sure, let me just tell you this, there will be always tolerances between the elements, whatever we really install in. So usually a precast to precast member, you will always have some tolerances. So this tolerance is the one what we usually, once we fill concrete or something, it gets filled up. But even then, the way we design is like saying that the dowel which is in between here, exactly at this point or here, the entire force or whatever we calculate, as I explained you in the previous slide, the entire force or the shear will be taken by the steel. That is how it will be calculated. These are some of the typical connections what you see in a double wall. The first one is like a typical wall to column connection. Um, a double wall connection is always easier, so that you can just use the same bars, whatever is there and then do it. Similarly, a corner connection. Then there's a 3 wall type connection, wall to wall connection, which is just a horizontal connection. Then there's an end detail here. So I think like these are some of the standard practices what we use when we come across a double wall kind of a wall in construction. But generally we may not find double wall everywhere. So because procuring this double wall mold itself is a costly affair. So I think like we may have to deal with a lot of solid wall connections and those things, which I'll be dealing in future. The next thing what we also see is like the column to beam connection. So one has to understand like based on the analysis, whatever we do, there are like different kinds of connections what we can achieve it. So usually our buildings we tend to do a kind of a moment connection between the columns and beams, which is largely accepted. And in order to achieve such kind of connections, so what we do here is like the beam spans between column to column here, and then it will be actually resting on the corbel. We'll deal about a corbel a little later. So between corbel to corbel, there shall be protruding bars. If you see this, the bottom bars will be protruding out from both sides, and this is only a precast part. Whatever you see is a precast part, and there'll be at least another 70 to 100 which will be left over for the diaphragm to get connected. So these protruding bars, apart from the bars which will be installed as the top bars at the top, will act as a moment connection. This gap, whatever you see here, this gap or whatever you see in the photograph here, this gap will be poured with concrete, which is called as a wet connection. So if this is the plan view of the entire connection. This is a kind of a section view of what you see here. So this gives you a complete rigid kind of a moment connection, which what we usually see in the other buildings also. There is this is how a detail would really look like. So you will see the bars coming out here. This is the wet connection here. The top bars will be uh, installed inside above the precast member, and then whatever the kind of moments we encounter at the supports will be taken care by these bars, and this will be installed inside. This is how the connections are achieved inside. The next thing is like just a hinged beam connection. This is like I think like most of it. The problem is like how we go ahead with the analysis. Um, we would always like to have a dual system working on. So in such cases, I think like we need the moment connection to work in. If at all, if we have a luxury of having a lot of shear walls everywhere across and everything, and there is something what we can also use with kind of a column to beam, which is a hinge connection. Here, in such types, what happens is we can have a column which can be at least like double height or triple height lengths. So here, the pace of construction will be much more faster because your columns are standing for about 2-3 levels, and the uh, uh, the corbels will support the beams and the beams will support the Holocaust. This is a simple connection. There will be no protruding bars which will be coming out of the beam, which will get into the column. So, what are the see when we are talking about beams? There are like a lot of things what we have to literally take care in terms of the beam design. So the first thing is like whatever beams we design, all the beams are analyzed as a separate case. See, apart from whatever you do as your first model, there'll be so many other cases what you'll have to analyze for the beams also. As a separate case, we'll have to analyze the beams as a hinged beam and design it for self-weight itself. Uh, and for the slab and the construction line load, because usually this will be usually for the longer span beams, because once you put it on top the corbel, you would have still not achieved any kind of wet connection or the moment connection between the column to the beam. It will be resting on the corbel. So the beam at that point will still be acting as just as a or the ends will be or the supports will be just as a hinge point. There is no connection there. There is no fixity. So in order to that, what we do is like until the wet connection is complete, I think like the beam acts as a hinge. So that's the reason these loads are, or this is one of the cases what we have to consider in. The beams are further checked for the live load and dead load with the factors, and all the relative seismic or the lateral loads are also checked for. Apart from that, the top reinforcement, what I have shown in the earlier figures, that is nothing but the reinforcement for the moment resisting beams are checked again for the other cases, and all the lateral cases are being checked for that. And those are the lateral bars, whatever we give. I'm sorry, the top bars, whatever we give, are for those connections. So once what we have to take care here is like the beams, what we design. Um, Once the beam is installed on the corbel, the most of the dead loads of the beam and uh, the slab system is already um, is already into the system or already into the frame. So the protruding bars, whatever we see on the top, should be only designed for the lateral load cases. You don't have to design for the entire forces coming in. So because the load would have already been passed on to the columns. So one has to ensure that you can just reduce your rebars there. So that's the way we can do it. And the top bars, whatever we design, can be only for the moments what you see, which will be experiencing from the lateral loads. The other kind of connections, what you see is like, as I already told you, where the beam will be carrying the hollow cores or the systems. So this is like an L beam, and also a kind of another thing is like your inverted T beam. You will see hollow cores on either sides, and there'll be a topping on the top. So one has to also ensure that whenever there is a kind of like a screed or something which is going to come on, especially when you see this hollow core bed, you need to have a kind of a broom surface so that there's proper bonding between the new concrete, whatever you wish to have. The Now let's come to the corbels. So the corbels are the main important things, the kind of system what we use in the construction of precast. Corbels can be analyzed in two ways. One is like the cantilever beam method. The other one is the strut and tie method. Here, this is a very simple method what everyone follows, and I think like the design is like far well known. I don't have to elaborate on that one. The things what you have to take care here is like uh, the corbel can be designed only for the in terms of wherever the moment connections are coming in. This can be designed only for the dead loads or the construction loads what comes in when you are doing the installation. You don't have to design your corbel for the entire complete load, because if you are doing a moment connection, the corbel is required for the beam to be placed on the corbel, and then the hollow cores will be placed in the beam. So once this is done, the load path of that dead loads has already gone to the column through the corbel. So then the protruding bars, whatever you have on the beams, where you do the wet connection, these connections will take care of all your lateral loads. So you don't have to design your corbels for the entire load. This is my view here. The other method, whatever I told you, is the strut and tie method. Is also like a kind of a way of analyzing the corbel. So it is up to the designer to choose whichever is comfortable the cantilever beam. So what all we should also consider doing this. See, one has to see that when we are using it by itself, because pre-stress force, it just upheaves by itself. So once this is done, and when you're resting it on top of the corbel, there's every chance that there is lesser bearing what you see on top of the corbel. This has to be properly analyzed. What happens is, when you have a corbel of a certain width, say it's usually around, say I'm just picking up a number right now, is like around say 150 kind of a width of the corbel, which is here, um, then what happens is you'll have to have your tolerances of like around 20 any member. Apart from that, once you have a 20 and due to this kind of a camber, whatever this member achieves in, you may not have a complete bearing on the corbel. So one has to ensure that whatever is the bearing surface available is sufficing the bearing loads. So we have to ensure that one, and then go with the proper detailing of this, or see increase the width of the corbel so that the structural members are completely bearing on the system. Apart from this, there is something called as the wall shear wall discrete connection. Here, shear wall discrete connections needs to be achieved at every floor. So what we do is we consider the maximum shear, or whatever is acting on the wall at every floor, the story shear. Therefore, the wall is and the shear wall to the screen connection is given. Also, this is like due to the kind of shear, because these are elements, individual elements, there'll be something like a kind of an overturning effect can also be happening there. This is another check what you have to do. For the check of overturning, what you have to do, you have to have the resisting moment, which will be a factor of your dead load. So finally, you have to ensure that the kind of doubles whatever you give, or the net moment what you incur from the tensile or the compression forces is totally countered. We have to do install the doubles based on this particular force, considering the dead weight of the member also. The final, important connection what we see is like called as a shear flow connection. This is one of the most important connections what we deal with in the precast construction. So when we design any kind of like shear walls, we actually design that as a kind of a member where it is combinedly taking all kinds of loads. So if generally we see this as a lift core or a stairwell or whatever is there, usually it will be a C-shape. There can be also walls which is like the other shapes also. But I've just taken for an example just C-shape. There can be something called an L-shaped wall, or also a straight connection. So this particular shear wall, when we have to literally transfer the shear from one wall to another, the way we have to achieve it is by something called as the shear flow connection. It has to be done by VQ by I connection. Here, where the Q is nothing but the first area of moment of inertia, and then the I is the moment of inertia of your intersection. So I think like this is we have dealt this in our mechanics classes. So this we have to ensure. So whatever for the shear flow we get, the dowels are given along the height of the wall to get connected, and then the connections are possible. Then we have to deal with kind of a diaphragm. See, the other thing is like when the hollow cores, the beams are all placed, there is one layer what we have to literally concrete, something like around a minimum of like I think IS code specifies 50 mm. We generally use between 70 to 100 mm. 100 mm because at times when you have pre-camber in the system itself, or in the pre-camber in the long span Holocaust, at the center you may not get the required thickness of 50 mm. That's the reason like an average of like around 70 to 100 mm is what we generally recommend. So how do we do this? So the story shears at that particular level has been calculated, but the story shear at the top, wherever the at the terrace is always the difference between the story shears is there is higher. So we usually take that one, or maybe if it's a very tall building, then we take it for every 4 or 5 floors at once. So this story shear is actually like then distributed over the length of the perpendicular length, whatever you see here. So based on that, you just design it as a deep beam kind of a concept. So based on that, whatever the steel you get, you give it as a kind of like a cord tension of the cord steel, on the either ends, that is on the either ends of the structure. Here also what we do is like when the entire load is applied against the system here or the lateral load, we also consider the supports. The supports is like these are the supports which is like between two frames, whatever you get here between building to building on either ends. So these can be considered as supports, and whatever the maximum bending moment you really get from this is what we design as a cord steel. Now let's get into a kind of like the handling and lifting part, which is like one of the most important part of the precast industry. So we always deal with heavy kind of materials, which will be like uh, varying. I think like basically from about like 2 tons to like maybe about even 10 to 12 tons. So one has to have a proper knowledge of what the element weight is. We should know that what the crane capacity in the site is used. So based on that, the designer has to actually uh, design or even detail that particular kind of elements based on the limitations what we have. So what all the things we have to see here. The loads and forces on the precast and pre-state members component during production, transportation, and erection will require a separate analysis because the concrete strength at this stage will be much lower than the support condition and will also vary compared to the final in the service position. See what happens is when you start as soon as you like cast the concrete, you would like to demold it and then you would like to transport it. But there is every chance that this concrete won't have achieved its complete strength. So that's the reason what we have to do is like we analyze this structure separately, or like whenever in the ETAP itself we just give it as a different case, analyze it for its dead load and see whether the span moments are good enough and for a lower strength. It cannot be designed for its design strength. So we have to reduce the concrete strength, see how the concrete how the member behaves, and that is what you have to detail it when you are giving it to the shop drawings. This will be an additional steel may require, or whatever is there should be detailed. So apart from that, we have to see how the transportation is done, because you can't just give something like about a huge um 20 tons or 30 tons or whatever is there on a truck, because I think like there's a maximum limit what even a truck can take. So I think like there'll be some limited amounts of uh, 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 load capacity. Based on that, we'll have to design the members too. Uh, Apart from that, when you design your building, you should also know where your crane is positioned, because the radius of your crane at the tip is where maybe if there's an element where which has to be installed is really heavy, then you have to take care of like what load can the crane take. Based on that crane, you'll have to actually maybe design or even cut down or maybe do a kind of like a half cast kind of a beam or whatever is there or whatever element you're dealing with. We have to look into those aspects. So how is the usual lifting hooks are given? So this is just a pickup from the PCI manual. So this gives for a typical panel, and also for the slabs, whatever you see, there are like a 4-point pick, and there's also like a 2-point pick for a vertical and also for a horizontal pick. Apart from this, there are other lifting conditions. Suppose you have an opening where you may have to give some kind of a supplement member during lifting conditions. So this will help the entire member to act steady, so that you don't have to, I mean, you don't see any kind of cracks in future. So with all these things, what we do is like we develop a kind of a 3D model. So all the information has been put in, we have designed it, all the connections are done. We know how the lifting techniques is going to come in. So with this, I think like there are like a lot of other softwares like maybe Revit or Tekla, whatever is there. We develop a 3D model. Here I'm just showing one of the small models of a villa what we have recently developed, and uh, one can see like every detail, every joint, everything has actually been uh, detailed here. So one can imagine that if a small villa like this, which is about like not more than about 1,400 square feet, um, there's so much of detail there. I think like you should imagine what are the details what we have to work with a real big commercial buildings. So here, what we had also done is like we went ahead and designed a precast footings also, because this is a small villa with a smaller this thing, and with the side cast, one can see that we had developed uh, footings along with the walls, and at this point, at this junction, we had a wet connection which was done here, and these are the molds, and you can see uh, the live footings which is right up there, which was installed. So some of the shop drawings what we deal with. Um, so this is the typical foundation drawing, and the details, every detail, every rebar is captured so that all of us will exactly know what's the consumption of the materials we are going ahead. Um, this is a wall detail. These are like temporary bracing what we give at the openings. There are something like all the MEP inserts are all shown here. So this is a coordination level what we do it, and then the doubles which gets connected on the top. All these things are shown. So this is another wall. Along with there'll be like cross ties at the openings. Uh, all these things will be detailed, and you will exactly know what's the kind of consumption we are going ahead. This is one of the main advantages in precast, where we don't have to literally bug on like saying like what is the amount of steel we have to use later on. There'll be a lot of arbitrations which happens on this, usually in cast sensitive big constructions. But in precast, I think like one will have a pretty good idea of what is the amount of concrete and steel consumed. So this is the villa what I showed you a 3D model. This is a villa what we built. There are like about 50 villas coming up right now, and this entire villa was built in 15 days. This is one of our kind of achievement what we did. The superstructure was built within 15 days with the precast technology. So we were also dealing with a lot of joints, uh, with a lot of joints and everything. And the thing is like we have to treat these joints. The joints uh, have to be in such a way that all the column connections and all the intersections between the column wall slabs have to be treated. So usually what you do is like you do a connection uh, using a non-shrink grout. So this non-shrink grout gives a very good uh, durability characteristics, and such that you don't see any kind of leaks. So I think like there are a lot of grouts which are available from Sika or even Fosrock. I think these are the kinds of non-stick grouts what we use for the joints. Now this is just a food for thought. Like I just explained like whatever things we what we do as like saying that more complicated things, but in India, I think like we have age-old structures which are like centuries old, and these are all like monolithic construction. What they have done, there you can see like columns, you can see corbels, you can see beams. I don't know what connections they've used. I don't know what is the lifting technology they've really used. Um, these structures have really experienced all kinds of seismic or all the climatic kind of variations, but it is more stable than whatever we do currently. I think like we should design such structures, or we should learn a lot from these kind of structures. So I would really see that there's some research done, and such connections are really or such buildings are built so that we can have structures which are like long lasting, and I think like one has to understand what kind of connections they really use. I really don't know. Maybe there will be some research or someone would have really gone through this. We should literally take a look into those things. Maybe adopt into our technology and then improve our own kind of knowledge. Um, so I think I have covered whatever is possible from my side and whatever the industry does. I would really thank the BLDA college for me to giving me a chance to express myself with respect to the precast construction. Thank you very much. If there's any questions anyone would really like to pose them, yeah, I think like we can just go ahead. Thank you. Hello.
Thank you, sir.
Thank you.
Any questions? I'll just give permission to unmute. You
Yeah.
can just unmute. Now, participants have permission to unmute. You can unmute and ask for any questions. I think in the chat, we have questions. It is very interesting and informative session. I really enjoyed. Thank you, Srinivas sir and BLDA College by Ruti. Another from Anvita Sinha. There is a question: what should be depth of foundation for that structure? Which structure? I don't think so. What should be the depth of foundation for that structure? Which structure?
Okay, let us just assume. I think probably I just showed her one of the villas, whatever
Okay.
is there. So I think it is definitely very similar to what we do in the conventional construction. There's nothing special there. Based on the safe bearing capacity, what we have really achieved, that is where the foundation was actually laid, and the analysis was done very similar to what we do for the casting structure. So whatever sizes we achieve, we have just converted that into a kind of a precast member, and we have checked the entire elements such that it can be lifted and it can be handled easily. That's it. Any other? I guess that is the question she wanted, or if there is anything else, I can definitely go to.
Any other questions from the participants? You can unmute yourself and you can ask the question to the sir. What should be the minimum grade of concrete? From Anvita, participant Anvita Sinha, what should be the minimum grade of concrete and minimum grade of steel for PSC?
The grade of steel is always the same thing. We don't have to change the grade of steel. I think like I've already shown you what's the grade of concretes what we use. This is the minimum grade what we use. I think like whenever we are dealing with pre-stressing or pre-stressed members, I think like minimum grade is always M40. Suppose if we need kind of other these things, yeah, we have to increase. I think like we have used until the M60, especially for kind of wall systems. I'm sorry, for the columns and also like even for the shear walls. So this is what we use. I think like maximum is M60, and it ranges between M40 to M60. The reason is like the reason we require a higher strength, as I've already told you, is because we need to demold it very fast. I need to demold it on the next day so that I can accommodate the next casting to happen on the same mode. Else, we'll be just wasting our time, and then the precast industry, which really boasts about like saying that we can finish the structure faster, really comes down. This is a um, uh, kind of a mantra what you do in precast. I hope you're looking also at my slide where we say what is the concrete grades we use.
Yes, sir.
Yeah. Anyone else?
Sir, one question from me.
Yes, sir, please.
Suppose during installation you have some impact on the element. Suppose while erecting a beam or and erecting a column, you have
Yeah.
some impact during installation. Is that been considered in your analysis and design?
Generally, no, we don't, because see, suppose I'll just talk about right now with just with respect to a precast structure, not with a pre-stressed member. In a precast structure, what we do is like, see, it would have been designed for the ultimate loads or whatever the loads which really comes in. So during lifting, it will be the only force which will be acting will be the dead weight, and if there is an impact, whatever is there, I think like the impact load is definitely not considered when we are designing, because we would say that we have to be careful when you're handling this. Suppose if that happens, then the only way is like, and if there is any detrimental effects on that particular member, we have to recast it. Or just including that impact factor into the design will actually like increase the cost of the member itself. So that's the reason we really don't put that across. Hope I've understood you. I mean, I've answered your question.
Yes, sir. Thank you. Suppose you have some lateral load. How is it safe, the precast elements with the lateral load?
No, but that's a reason. Like all lateral loads. I mean, every lateral load is taken into consideration. Um, So if you literally see when I explained you with respect to the connections, when we do this moment connections or whatever is there, so the beams or the columns or whatever is there will be designed as per whatever you uh, do as in a cast institute structure itself. So all your earthquake loads, everything, including your wind loads, everything will be considered and it will be designed. The rebars will be for that. There is no kind of any uh, what do you say, like a leeway with respect to that. We don't consider this, we don't consider, no way. We have actually in fact designed, I think, like the hospital structure what we have designed in Coimbatore is in zone 3, and in fact we have also done all ductile detailing, everything is done in that. It is very similar. I mean, you don't have to, so suppose when you see a finished product, whatever comes inside the beam in a cast structure will be very similar here, except for some things. What we have to do is like where the how the lifting would really occur, or how it really behaves when you just place it without any kind of moment connection. Those things we'll have to analyze, and then we have to take care of all these things and then give us a final element. There's
And
no compromise on any lateral forces.
thank you for this answer, sir. Another question from me again. You
Yeah.
have been involved in many projects. Now, suppose for one complete project, is there any element which has been failed? What is the percentage you say, or all the elements have been erected without any what you call failure? I mean to
No.
say there might be some failure wherein you have failures while erection. I'm talking.
Yeah. I mean, see, there's, I don't see that I have 100% clean record. It never happens because see, there are so many people getting involved. I could also like see there was one case where we could see that it was a priestess beam. It was a priestess beam, and then we had a kind of small cracks which had come up during installation. I mean, not during installation, during the final stages when all the loads were transferred. So we had to actually analyze like why this had happened, and we can always fix this. It is very similar what we do for the other structures. You may go with like carbon wrapping, or you can do something and retrofit that particular member. That's not a big thing.
But that will also cost additional. Will this be
Oh,
cost
yeah, see,
included into the project?
at, at that point of time, it is a builder's responsibility, because we as a builder, we have to take care and we have to give a complete designed by, I mean, like a complete solution or a complete stable structure, yes, it is definitely a part of what do you say? Maybe some lacuna somewhere. Once you see that, you have to rectify it and you have to go through. Even if it is like any other structure, the contractor has to bear it, or the contractor or the designer, whoever fault is that, has to bear it. We have to do it, and we have done it.
Thank you. Another is you have many safety. Safety is a main part while erection.
Yeah, yeah.
Is there any safety
I
breaches which you have encountered in any of the project?
um, See, I dealt this particular presentation with respect to like more on the precast and its design and the connections. Yeah, safety has to be followed, and that's a far most thing what we have to do, because we'll be dealing with very heavy elements. Usually, let me tell you, like that's the reason I had a very small topic on how the lifting procedure goes in. So the exactly where the hooks really comes in. So apart from those hooks, whatever is there, I think like the cranes and the belts, whatever you have to use, I think like there'll be a safety engineer who can take care of all those things. I've not dealt with that part here, but it is of prime importance. It has to be done, and until now, I've not come across. I think like any kind of a in my whatever the precast tenure is or wherever we are built, I've not come across any failures in those things where the belt has given way or something has given. Because even those, what we do extra checks apart from this one is like we also check for the punching shear and everything, where for that particular grade, so that the hooks don't really come out when you really lift it up. Or the other checks, what the safety engineer has to be on site who does that one. uh, he has to check on all the belts or the chains whatever they use, and the crane capacity whatever you use with respect to the. That's the reason every shop drawing will have the element weight and whatever is there. So this information will be with the site project manager there, and he has to deal with it.
You have separate code for safety of precast constructions, or is it common? You have codes.
Um, I mean, literally, I don't know about this. I think probably it's like any other safety
Okay.
procedure you use. I think it's the same way. I'm not very sure on this one.
Thank you. Thank you. One question from Anvita Sinha. If using strong column and weak beam design philosophy, then if beams are of M60 grade, then column should be also of M60.
Absolutely, absolutely. We always use columns with the M60 grade. I'll tell you why we have to also use this one. Is like, see, I had earlier explained that the columns will have. I think like let me just go to that slide also. Yeah, here. See what happens here is like there'll be a lot of bars. I mean, protruding bars. What comes out. So in this kind of a system, we cannot have bundled bars or whatever is there. It's little difficult to incorporate bundled bars. So what we do is like we always use grout couplers or the kind of doubles whatever the thing is used. And when you use the sleeves or the 80 sleeves, what happens is you can only accommodate certain percentage of steel inside the column. So if I have a 25 rebar and there'll be a sleeve next to it because it has to lap very next to it, that will be almost like around 60 to 70 next to that. So you can, after that 60 to 70 you have to have another about 25 to 30 gap to accommodate the next rebar and the sleeve. So the percentage of column steel, whatever we get, usually in cast sensitive, we can I think like people can say that they'll achieve around even 4% or even up to 6% is according to the code. But I think like 4% becomes a very congested area. But in precast, I think like we limit ourselves within around 3%. 3% of steel, and then we try to accommodate this. And definitely we cannot have uh, 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 a weak column at all. It has to be strong column and a weak beam connection. That is the same kind of a methodology what we follow.
Question from Kannan. Is there any monitoring method to fix the module and elements in correct position?
Yes, absolutely yes. It has to be done. The precision is one of the most important things in precast. So module in the sense is like when you want to definitely have an alignment between uh, let me show here between the column and the beam. There are dowels which are actually sticking out of the corbels. These are the sleeves which will exactly fit into the beams. So this will give you a proper alignment. So we have to have this proper alignment. Else, again, we'll see a lot of other forces are kicking in. So and there'll be a lot of other laser instruments which will be used to have a proper alignment here.
One question from Tausif Attar. What about repair and rehabilitation of PSC structure? Repair and rehabilitation of PSC structure.
Or pre-stressed is that's what he means?
I think it. I think it means pre-stress, precast in precast.
See, one has to see what is the kind of repair it has to really require. I mean, suppose if there is some kind of a failure which has undergone due to some kind of a load, and anyway, as anybody would do a kind of a retrofit, one has to see what kind of cracks it has really developed in. So we have to see that. And as you say, I mean, like the easiest way one can really do is like by giving extra support. That is not acceptable, then we can have an extra steel beam coming in. If that is not acceptable, then the carbon wrapping comes in. So all these things can be done, and especially in terms of if it is pre-stressed member, we have to be a little careful, because once there's some kind of a cracking happens, we have to see what is the loss, and based on that we have to accommodate the particular kind of a design or do something for that one. That has to be done, and it can be done. It is not something that it is not done. So even if it is cracked at one area, it doesn't mean that the entire thing is going to just come down. We can definitely go ahead and repair and do that.
Any other questions? I think questions are over now.
Thank you.
Anybody want to have any questions? Okay, no questions. Okay, thank you, sir. Thank you very, very much.
Thank you. Thank you very much.
Thank you very much. On behalf of the management and principal, I'd like to extend my heartfelt thank you for accepting our invitation and for this FDP. And your session was such a wonderful. I had many questions to you. Actually, I didn't ask any questions to any of the research person. I had much interest in your topic. So thank you very much. This is a small appreciation from our college side. Please accept this e-certificate. Thank you, and we'll be touch with you for any such FDPs. Thank you very much, sir.
Thank you very much.
Thank you.
Thank you all.
Thank you.